Hello everyone, welcome back. So in this video we are going to learn about transfer function. Okay, so basics of transfer function. So what is transfer function, why it is used, and what are the advantages and disadvantages of transfer function, we are going to learn in detail. Okay, so generally what is transfer function? Transfer function will always gives you the mathematical model of the system. So it always gives the mathematical model of the system. That means, what does it mean, mathematical model of the system? That is, it gives the number of system time constants. It gives the number of system time constants. Okay, so it gives the number of system time constants. That is it gives the number of inductors and capacitors, which are energy storing elements again. So it gives the number of inductors and capacitors, which are energy storing elements present in the circuit. So we know that the time constant is the result of inductor and resistor, or capacitor and resistor. So each and every time constant here represents one of either inductor or capacitor. So the number of time constant represents the number of inductors plus capacitors, that is the sum of both inductors and capacitors present in the given circuit. So it gives the mathematical model of the system. Okay, so transfer function, so each and every time constant here represents the presence of either inductor or capacitor. Okay, so because time constant is due to this only, so time constant due to inductor will take it as L by R, and time constant due to RC circuit, that is resistor and capacitor combination, will take it as RC. So every time constant is due to presence of inductor and capacitor. So basically, what is transfer function? So what is transfer function is, transfer function is obtained from the system. So transfer function is obtained from the system only. So generally any transfer function, if a continuous time signal is there, or a continuous time system is there, so the system is represented by integral differential equations. So integral differential equations. Okay, so suppose if there is a resistive and capacitor combination here, so if you want to write V naught of t, so this is Vi of t, this is R, and this is C. So what can we write? So if there is a current flowing which is I of t, so V naught of t by Vi of t is equal to I of t into R plus 1 by C integral I of t dt. So this is one of the integral differential equation. Yes or no? So there is integration present here. Similarly, if you take inductor, there will be differentiation. Okay, so integral differential equations are present in order to represent the system, that is the transfer function here. The output by input is called as transfer function. So integral differential equation. So if you take the Laplace transform here, so if you consider the Laplace transform here, so V naught of S by Vi of S now becomes I of S into R plus 1 by Cs into I of S. So if you take I of S is constant, so common 1 plus C of S you'll get. Okay, so we don't get this Vi of t again, so V naught of t, so this we don't get, but as an example I'm telling, this is not exact analysis, but in order to show you how these integral differential equations are converted into algebraic equations. Okay, so integral differential equations are converted into algebraic equations. So this again there is a combination of RC here, so this RC combination is again converted into time constants. So it represents the number of time constants here. So this is the relationship between transfer function, time constants, and this is how integral differential equations are converted into algebraic equations by using Laplace transform. That is the transfer function concept only. So generally transfer function is defined as Laplace transform of output by Laplace transform of input by making all the initial conditions is equal to 0. By making all the initial, there will be some initial voltage across this capacitor or current across the inductor, because transfer function is always dealing with capacitors and inductors present in the circuit. So all the initial conditions which are present in the capacitor, that is voltage across capacitor and current across the inductor, must be made 0. So all the initial conditions across the energy storing elements must be made 0 before calculating the transfer function. Okay, or if you want another definition, so Laplace, it is transfer function is Laplace transform of impulse response. Laplace transform of impulse response by making all the initial conditions is equal to 0. Okay, so this is the definition of transfer function. Okay, so the next is the standard form. So the standard form representation. So standard form representation of transfer function. So the standard form representation of transfer function in terms of time constant is represented by C of s by R of s is equal to k into 1 plus s tau 1, 1 plus s tau 2, and so on, divided by s power n into 1 plus s tau a, 1 plus s tau b, and so on. Okay, so this is called as time constant form. Time constant form. And there is another form in order to represent the transfer function. So k into s plus tau 1, s plus tau 2, s plus tau 2, and so on, divided by s power n into s plus tau a into s plus tau b, and so on. Okay, so this is called as pole zero form. Okay, so this representation is called as time constant form, and this representation is called as pole zero form. Okay, so you can represent in both forms. Generally this k is called as system gain. So system gain is always calculated in time constant form only. Okay, so it is always calculated in time constant form only. So this gain is represented by this k, and this is represented in time constant form only. Sorry, something happened. Right, so if you are given with C of s by R of s, suppose you are given in pole zero form, like C10 into s plus 5 whole square divided by s into s plus 10 whole square into s plus 20, something like this. Okay, so if you are given with pole zero, this is called as pole zero form. Okay, so this is called as pole zero form. If you are given with pole zero form, so directly you can say that the gain of the system is 10. So if k is equal to 10, this is wrong. So gain of the system is not 10, because you can't tell the gain of the system in pole zero form. You can tell the gain of the system only in time constants form. So first of all, the pole 0 form must be converted into time constant form by taking so it should be in terms of 1 plus s tau. So it should be in terms of 1 plus s tau. So I am taking 5 constant common here. So if you take 5 common, what you will get? 1 plus s by 5. 1 plus s by 5, so whole square, divided by s into 1 plus s by 10 whole square into 10 square. I am writing outside directly, into 20 into 1 plus s by 20. So again you will get s plus 20 divided by 20. So this 20 will cancel out. You will get again s plus 20 only. Okay, so this is 10 into 5 square into 1 plus s by 5 whole square divided by s into 1 plus s by 10 whole square into 100 into 20 into 1 plus s by 20. So finally what you'll get? 25 into 10, 250. So 250 by some 2000, 250 by 2000 into 1 plus s by 5 whole square divided by s into 1 plus s by 10 whole square into 1 plus s by 20. So this is the gain here. So gain is now 250 divided by 2000. So 250 divided by 2000, so 1 8, so k is equal to 1 by 8. So gain of this system, gain of this given system is going to be 1 by 8, not 10. So you can't tell the gain of the system directly from pole 0 form. You have to convert that pole 0 form into time constant form first, and then we can tell about the gain of the system. Okay. So we have seen the transfer function in time constant form is 1 plus s tau 1, 1 plus s tau 2, and so on here, divided by s power n into 1 plus s tau a, 1 plus s tau b, and so on. So here k represents the system gain. So k represents system gain, and tau here represents the system time constant. Okay, t tau represents system time constant. Right, so when you have this, we can find two, or we can define two important properties of transfer function, that is order and type of the system. So order of the system is total number of poles present in the system. So total number of poles present in the system represents the order of the system, and type of the system is total number of poles present at origin. Okay, so total number of poles present at origin represents the type of the system. Okay, so suppose you take an example, c of s by r of s. I am taking a transfer function, so you can take either in time constant form or in pole 0 form. So I am taking in pole 0 form. So 20 into s plus 5 whole square divided by s into s plus 2 whole cube into s plus 10. You have something like this. Okay, so the denominator of the values of the denominator, making it to 0, it becomes the characteristic equation and it becomes the poles. So we'll discuss about poles and zeros concept in the next video. So until then, you just remember, so how to find the poles, making this is equal to 0, so s is equal to 0 becomes one pole. So here s plus 2 is equal to 0, so s is equal to minus 2. It is the pole of order 3 because there is cube here. Okay, so it is a pole of order 1, which is called a simple pole. Okay, this is again a simple pole of order 1, at s is equal to minus 10. So total number of poles here is 1 plus 3 plus 1. Total number of poles is 5. So order of the system, this particular system, is going to be 5. Okay, so if you observe, the number of poles present at origin is only this. S is equal to 0 represents the origin, and it has only one pole at origin. So total number of poles present at origin is called as type of the system. Since only one pole is present, so type is going to be 1. Okay, so type is going to be 1. So if there is no pole, at origin, then type is going to be 0. Okay, so type is going to be, if there is no pole at origin, the type is 0. If one pole is present, type 1. If two poles are present at origin, type 2, and so on. Okay, so type basically represents the number of poles present at origin, and order represents the total number of poles present in the system. Okay, so this is the concept of order and type of the system. Okay, so these two are very important. Basically type is more important because this concept will again come when we discuss about time response analysis. Okay, so please remember these two. And next is, what are the advantages of transfer function? What are the advantages in finding the transfer function? Okay, so the first advantage is we know integral differential equations are converted into algebraic equations. So integral differential equations are converted into algebraic equations. So this is one advantage, because we can solve the algebraic equations very easily when compared to integral differential equations. And second, so we know that C of s by R of s is equal to some will get in terms of this, like this. Okay, so I'm taking that as h of s. So what can we write? C of s is equal to h of s into R of s. Then C of t is equal to inverse Laplace transform of h of s into R of s. So this we can find by using partial fractions method. By taking partial fractions here, we can find this. So what does it mean? So for any given input, if you are given with some input, for any given input, we can find the output. From the transfer function. So from the transfer function, you can find the output like this. Okay, C of t represents the output of the system. So for any given input R of t, that is R of s, we can find the C of t, that is output. This is one of the main advantage. So this is why we are going to find transfer function. So if you find the transfer function of any system, so you can apply different inputs and we can obtain different outputs, and that we can calculate manually also. Okay, so this is the main advantage of transfer function. And third is, so from the transfer function we are going to locate the poles. So location of poles is going to be obtained, yes or no? So there is a pole here at origin, there is a pole here at s is equal to minus 2, there is a pole here at s is equal to minus 10, and so on. So for this example I'm telling you, so location of the poles is going to be identified. So when location of the poles is identified, we can comment on the stability of the system. So we can comment on the stability of the system, because we know that from Laplace transform, if all the poles lies in the left half of S plane, so if all the poles lies in the left half of S plane, then the system is going to be stable. Okay, then the system is going to be stable like this. This is a stable system because all the poles lies in the left half of S plane. So all the poles are lies in the left half of S plane, then the system is said to be stable. So stability can also be commented based on location of poles, and location of poles is again in turn obtained from transfer function. Okay, so this is the next advantage of transfer function. So all these are the advantages of transfer function. Then what are the disadvantages of transfer function? So what are the disadvantages? So first disadvantage is it is applicable. So finding the transfer function is applicable only when the system is LTI. that is linear time invariant. Okay, so it is applicable only for LTA systems. If the system is linear and time invariant, then only we can apply transfer function, or then only we can find the transfer function. Second, the initial conditions lose their importance. Okay, so the initial conditions lose their importance. Why? As I have told you, the formula here, C of S by R of S, or input by so transfer function is Laplace transform of output by Laplace transform of input by making all the initial conditions. So while telling you the definition, I have told you making all the initial conditions is equal to 0. So initial conditions also have an important role because they may make the system non-linear. Okay, so due to the presence of initial conditions, a linear system may be converted into non-linear. So initial conditions lose their importance. That means in the analysis of the system, the initial conditions are not going to be considered. Thereby, the perfect output for the system cannot be obtained from the transfer function analysis. Okay, so this is about transfer function. In the next video, we will see how to find practically the transfer function of any given electrical network. Okay.